talking about how buildings are going to be adapting to COVID. And let me give you a brief introduction of what this panel is going to be about. And with the COVID-19 pandemic, adapting and evolving buildings to effective mitigation transmission is a key resource for future to consider. We as team have been developing a house that adapts to the needs of the user and to compete and showcase to the SDME 2020, which is the Solar Decathlon Middle East, with our partners. And in this case, we have Arvinco, especially Prague, as part of our new upcoming panel series. As I said before, we have Farad and Rashoti, which is the lead building cyclist at Arvinco. So he will be giving a little bit of an introduction as well. And also we do have some of our team members, Scott and Kelvin. Hopefully Alex will join us after to discuss how we can, as I said before, buildings can be adapted to COVID-19 and how the indoor air quality can help us with a smart HVAC control and monitoring and interaction as well. So I will give the word to Scott so he can give us a little bit of a background of Team Team.
Thank you, Heiris. So as Heiris mentioned, we are a team of students from Heriot University who are going to be entering in the Solar Decathlon 2020 competition, now taking place in November 2021, as I'm sure all of you will know very valid reasons why. The house itself is solar powered, which is photovoltaic and solar thermal, so that's where all our energy comes from. But it's also, as mentioned by Heiris as well, as a smart house as well. So we're using extensive sensors and automation throughout the house to make it smart, but also interactive with the occupiers as well. This is where Arvinco come in particular. Their amazing sensors allow us to automate many different things throughout the house, ranging from lighting, heating, and air ventilation and circulation as well, which is obviously a very key issue as we're facing with the COVID situation just now. In the team, I am the sponsorship team leader, so I'm trying to build as many close links as I can as a team with as many companies as possible, and Prague has been very supportive of that with us as a team for the entirety of the involvement we've had with Arvinco so far, so I can only thank him for that. And I will pass over to Kelvin, who will explain a little bit more about himself.
Yeah, so quick introduction on me. My name's Kelvin. I'm one of the renewables team leads at Team Esteem. Just completed the masters at Heriot Watt and now working full time as well at the same time. I've been involved with a bit of part of my dissertation last year. Was involved with predictive modeling and part of the software side. So that's my involvement in software sensors. I'm looking to progress that as well in the future with Arvinco and develop a relationship there. I'll pass you on to Parag, who'll give us a brief introduction of himself as well, and Arvinco.
Thanks, Kelvin, and thanks, Heiris and Scott. So my name is Parag Rastogi, and I am a technical manager at Arvinco, and I lead the product, which is around indoor environment quality, monitoring, analysis, visualization, and reaction, and of course, controls. So it's the health, well-being, and controls team at Arvinco. My own background is in civil engineering. I did my bachelor's and master's at Purdue University in the States. I did my PhD at the Polytechnic in Lausanne in Switzerland, where I was looking at estimating the impact of climate change on buildings without exactly knowing what that climate change will be, how the climate will be in the future. So using simulation, for example, energy simulation. So since then, I've worked on, just uncertainty in simulation, and more recently, for the last few years, transitioned to looking at how do you collect real data about the environment in a building? What do you do with it? And how does it actually impact people's perception or health in a space? And we're happy to support Team Esteem, of course, being the Scottish entry for the only UK entry, maybe, but at least definitely the only Scottish entry to Solar Decathlon. And we'd be happy to showcase our devices, but also more importantly, explore how the team can actually teach us what to do with the data that comes out of those devices when you have a solar powered home in a desert environment or in a hot and humid or sometimes hot and dry environment. Thanks.
Okay, that's amazing. Thank you guys for introducing yourself. And now we are going to move on actually to one topic, progress on sensor and instruments in the home. It was supposed to be Alex talking about it, but I will give the one maybe to Scott or Kelvin if they want to introduce it.
Sorry, Harry. What was that again? Sorry.
Progress on sensors and instructions in the house.
Oh yeah, so I was just going to cover our basic progress on from our softwares and sensors team. So we recently had a D4. One of the deliverables for the competition was recently for a resubmission, and we had to restructure the entire software plan, work out where exactly in the room the Arbenco sensors would go, how do they interact with the gateway, and then also look at OpenHab. So OpenHab is an open source automation system for IoT, and we've been looking at various ways and how we can interact with the Arbenco API, looking at the user interface, sorry, and the OpenHab and how the difficulties in the software of like connecting that. So we've been looking at various sort of IoT things we can implement into the house to use the automation software with Alexa, such as smart bulbs, different kinds of like switches, dimmer switches, and what kind of capabilities we need, and making a whole list of looking at costs, capability, and energy efficiency. So we can make a house that's using these devices energy efficiently, as well as being able to have the capabilities of using them to incorporate our smart control algorithms later down the line. That's the sort of stage we're at with the software and sensors and OpenHab, and as well as looking at different sort of interactive faces and screens in the house. So example, looking at smart mirrors where we can display like date, time, weather while you're just going in the bathroom. So it makes it sort of a seamless interactive experience just living in the house. So that's the sort of things we've been looking at and trying to innovate in ways and stuff like that. So that's just a quick brief overview of our progress so far on that side. And I'll pass you on to Haris for some more questions.
Yeah, of course, that sounds so amazing. Now, I will be asking some questions about then COVID-19. And the first question is good air circulation from smart controls more effective than social distance at minimizing COVID-19 transmission risk levels? I'm going to paste the question as well so you guys can read it.
Yeah, sure.
And if any of you would like to talk about it.
I can jump in on that. So I think it's I would not go so far as to say that good air circulation is more effective than social distancing. Both have their place, right? So social distancing cannot be replaced by better air circulation. Right. So first of all, just for those of you that are not particularly familiar with the main routes of transmission of COVID, there is aerosol. So when you're in the air, when viral is literally aerosolized like a spray. You have droplet. So when somebody sneezes or ejects a virus particle, and the big water droplet lands on you containing the virus, and then you have fomite. So from you sneeze or you somehow transmit the virus to its surface, and somebody else touches it, and then they ingest the virus. So we're talking about the difference. Social distancing is very effective against droplet transmission because, of course, you're too far away for that droplet to stay airborne until it reaches you. And good air circulation is really effective against aerosol transmission, where because you're effectively removing some of the virus-laden particles out of the space by chucking indoor air outside, right? And when you bring in fresh air from outside, you're obviously diluting as well let's say the pollutant, which in this case is a virus. So yeah, to reiterate, it's not necessarily more effective. They're sort of complementary. And depending on the situation, you probably need both.
Yeah, I was just going to say there, is that from your experience working with office buildings, essentially, or commercial institutions? You found that, because I've seen ANSYS models for CFD looking at the transmission distance and how the gravity just brings it down a lot if you're a certain distance away. But I don't know the effectiveness of good circulation, but then I guess that's what you covered there.
Well, yeah. So it is based on our experience. So we developed a guideline. We published a white paper on this. It's a guidelines on how to effectively manage, the different kinds of transmission in buildings, looking mostly at the air side of things. So we're not experts on fomite transmission by any means, right? And what you say about sort of CFD simulations of how far a droplet can travel,
Yeah.
so that's where the rule of thumb of 2 meters comes from. If you're more than 2 meters away, you're probably not going to have a droplet reach you, unless of course somebody's singing or shouting. So those is different situations where the droplet can go further, or sneezing. We were looking, aerosol really becomes an issue when you have people that are, especially when you have people that are they're not showing symptoms, asymptomatic. Because then you're literally just breathing particles in and out. You're not sneezing, you're not coughing, you're not doing anything special. And so we did some simulations ourselves with certainly blanking out on the name of the software. It's a very common software, and it'll come back to me eventually. Contam, that's the one. Contaminant simulation transport, right? And we looked at the fact that when you have, you can't predict how many infectors would enter a room in an enclosed space. But if you make assumptions that, okay, how many entered, some percentage of people are infected, then you can calculate what the evolution of the probability of infection is in the room over time. And that's where we found that, going from the lowest level of recommended ventilation to the highest level, according to CIBSE. So CIBSE is our professional body in the UK for HVAC. You can actually cut the transmission rate by probability by about 50%. So the air circulation is a very effective thing for reducing the probability of infection in enclosed spaces.
I was just about to ask as well, the different kinds of ventilation, things like that you get can make a huge difference as well, can't they? So like displacement ventilation as an example is generally deemed a very effective way of removing aerosols and things like that, just because you are pushing all of the air out continuously. So that's obviously something to have a look into as well, isn't it?
Yeah, and the latest guidelines for COVID from CIBSE, for example, and ASHRAE, which is the American equivalent, or REVA, which is the European one, is basically to maximize fresh air. So, keeping in mind and a little bit of sort of historical context, ventilation guidelines have traditionally been sort of set to sort of minimum standards. That's the standard. It's sort of to prevent the situation where when you walk into a room, you can smell other people. So you shouldn't have to smell other people, right? So it's really setting the floor. So COVID sort of turns that on its head because now suddenly people are emitting not just CO2 in a space, they're emitting lots of virus particles that will, we've always been doing it, right? This was a problem when measles was around, and when measles is still around, but when it was a bigger problem and other viruses. So the problem won't go away with COVID. Instead, now, of course, the recommendation, at least temporarily, is to run completely fresh air sort of regime, which of course is very energy intensive in extreme climates, right? So you have, winter is coming, and the winter is here actually, and it's quite energy intensive to run fully. So what, for example, one of the optimizations we proposed was, well, if you had sensors like the Teamhouse will have, you can actually measure when you've reached nearly fresh air levels. You do a proxy through CO2 measurement. And so beyond that, is there any point running ventilation? Well, probably not, because you evacuated all the breathe air from that space. And of course, though, but in isolated like dead zones, and if I literally come face to face with an infected person, then of course ventilation has no role to play, because it's droplet transmission. Does that answer the question you were going for?
Yeah.
So.
Thank you very much. That was very interesting to hear. Thank you. And we do have another question. And how effective is UV light in reducing COVID-19 transmission risk within indoor environments? And any of you can take the word.
Well, I was going to say, let me just reframe the question slightly. How effective is UVGI? So you ultraviolet germicidal irradiation, right? That's the full thing, which has been around, by the way, for 100 years. At reducing the potency, the load, the viral load because basically UVGI kills viruses, right? So it's not, it's indirectly responsible for reducing the probability of infection within transmission within environments. And the way that it does that is when you have a batch of air and you irradiate it, then if there are viruses in it, they will die, right? Or bacteria, whatever it is. Which is why, but of course, remember that UV light is also harmful to human beings, right? So you can't just have, people being irradiated by UV in a space. So normally what you do is you put it at the top of a room. So it's, upper room. So, if your ceiling is high enough, there's a zone where nobody ever goes, right? There's a sort of air gap which nobody ever touches. And so you can just do it there, for example, which is quite effective. There are some classical experiments going back to the 20s, which showed that, if measles could be effectively, the infection or reinfection of measles could be very effectively prevented with UVGI. And now there are several options for incorporating it straight into your HVAC system. So as the air passes through the HVAC system, it gets, disinfected with UV. And in fact, there are now portable UV devices that you can buy, for a couple of £1,000 actually. They're quite expensive, but you can sort of wheel them. You can imagine wheeling them into a hospital room when everybody's evacuated, irradiating the space, waiting for it to, ventilate, and then moving everybody back in. Right?
Yeah, I was going to add, I think we can have the case for using UV light maybe in the Esteem House, because as part of, after the competition, the house might be there for several more months or weeks. And basically, people will be coming in and visiting all the time. So it'd be maybe good to test, or as a test bed for the UV light, to get other data from when people come, a group of people come in and then leave. We UV light the entire place and see how less the viral load reduces when the next group of people come in. That's where I see potential that we could, innovate or adapt to COVID in the Team Esteem House anyway.
I was just going to ask Parag as well, the relative efficiency effectively, because obviously if you're trying to get all of the air in a certain space, so if it is, as you mentioned, integrated into the air conditioning system, that all the air that comes in goes through the UV light, how long does that take realistically to try and replace all of the air that's in the building? Obviously, I know you've got flow rates and things like that, but if you've constantly got a lot of new people coming in, you've got a very high load essentially of a lot of air needing moved about a lot of the time.
Yeah, absolutely. I think you both sort of hit the point right. Is that if you have portable systems, they're really mostly effective. Whether it's for it's also true for particulate pollution, right? When you have dust in the air, right? So what the current recommendation is, these are probably effective when they're placed right next to a human being somehow, and they're talking about a very limited air volume. But in the case of the Esteem House, if you have the mode, if you have the mode that Kelvin described, where a group of people comes in, they leave, and then there's a break for 15 minutes, during which you can disinfect the space. That's more effective certainly than people just constantly coming in and out.
Yeah.
Which is for any point source, not point source, a point cleaner, which is just a mobile cleaner. It's just trying to cycle the air through itself. It's probably not going to have the capacity to constantly refresh the air as fast as it's being churned.
That is very interesting. Wow, I didn't. Thank you. And now we will be moving on into indoor environment quality sensing. So what is distributed sensing and why is it so effective? Again, I'm going to pose the question here. So why is it distributed sensing? And what is distributed sensing and why is it so effective? And Scott, Kelvin, or Parag?
Sorry, it always takes me like a half a second to go and realize that I'm not unmute. So it's okay. So distributed sensing usually means putting lots of relatively sort of medium quality sensors, right, in lots of different places, so sensing all the time, everywhere, right? So what you're going for is you're going for high spatial coverage. You're covering a lot of the space, and high temporal coverage usually, right? So that's also like as in time, you're measuring with the frequency, with high frequency. So this is the reason distributed sensing is effective is because what you're trying to measure is a very complicated and complex phenomena, which is the change of the indoor environment and the dynamics of the indoor environment in a space, right? Now, there is of course an argument for, buildings don't change that fast, right? So we're not talking about temporal frequency of like a hertz, or 100 hertz, like you do in controls or in electronics. But you could get away with every hour, every half hour. So of course, that's somewhat domain specific and application specific, but generally distributed sensing helps you identify problems that are otherwise invisible, right? Because if you don't know that there's a problem, you're not going to put a sensor there, right? So, but if you don't know what you don't know, and the only way to find out is to have sensing all the time, everywhere. And it's effective also because it provides, not only does it provide visualization, it then lets you act on that. Right, so it lets you visualize the air state or the pollution state, and then you act on it. So, for example, you install UVGI, you install filtration, you turn up the ventilation to reduce the CO2, and then you can see the impact of it, right? Which is why it's useful. In the Team Esteem House, and what we found in our own research with University of Strathclyde, and I'll quote our collaborator, Professor Tim Sharp, is measuring, just having one sensor, let's say in the living room or the kitchen, is not a very effective way of telling what's going on, what the dynamics of the different rooms in the house are, right? So if you think about the domestic activities that actually generate pollution, so cooking is a big one. So if you put this sensor in the kitchen, you would measure the cooking, off gassing and so on. But you won't measure, for example, the fact that if your bedroom is badly ventilated, your sleep is affected. Because the high CO2 level means it's bad for your sleep. And for example, Tim and his team at Strathclyde, and when they were in Glasgow School of Art, they mentioned that they measured very, very high, like sort of unhealthy levels of CO2 at night in Scottish homes. Because obviously, if you're feeling kind of stuffy and you're awake, you can open a window. But if you're asleep, you're not going to get up to open it. It's highly unlikely you'll get up to open a window. So, in most cases, theoretically speaking, we're talking about, it's like an application of Shannon sampling theorem, right? If you need to measure a signal, you need to measure it at least at twice the frequency. So if you think along the same lines, if you have a unknown phenomena that you're trying to measure, then having more distributed sensing in space and time is obviously going to help you identify it better. Right?
Yeah, I think with having distributed sensing and having the better time resolution and spatial elements to it as well, is good for homes, because especially now that everyone's working from home and you have to be, on your ball, you have to be proficient in your work, comfortable in your environment. So having those cheap, loads of distributed quality sensors, that can give you those control mechanisms for reducing CO2, I think is really applicable today as well. And something that we should probably look to adopt into the house, I think.
Yeah, no, it's very interesting. Scott, do you want to add anything?
I was just going to say, I completely agree with what Kelvin's just said there. The fact that you can get almost an up-to-date system diagnostics, essentially, of how your house is doing, rather than just individual rooms, is so important in the modern world with the way we're building as well. So obviously, with the way construction's going now, of everything's as highly energy efficient as possible, there's no breathability in buildings. So as you mentioned, Parag, if you suddenly have a massive amount of, shall we say, pollutants are given off, so if you do have a lot of people maybe working out, doing a lot of gym stuff as they are now at home, that stuff can get kept in the house for a very long time. Whereas older buildings were meant to be breathable and have natural airflow coming in and out, and it made the buildings more pleasant. And it ties in directly to sick building syndrome that everyone's having with new builds in the past 10, 20 years, because this was something that wasn't considered before, was, all these gases that everyone's given off, all the pollutants and harmful VOCs that are trapped in these new builds, they're not actually getting out all of a sudden. And being able to record that, and as you're saying previously as well, Parag, of having the ventilation to be able to move that all around and replace it is really important. And I think that ties directly with, even as you're saying, the point of being able to sleep properly. If your room is so tight that everything you're giving off and there's no replacement of air, you're going to have a nasty sleep more than anything. So yes, no, I think it's brilliant.
I do have a question, and I think it's very interesting. Do you find green walls effective ways? Do you find green walls effective ways of minimizing CO2 levels and improving indoor environmental quality? I posted the question as well, so you can have a look. But it's just like very interesting how maybe your point of view of green walls.
I'm happy to take this one first if you want. So it's funny that you put that one in because that's what I'm looking at as part of my dissertation this year is the effects green walls have on indoor and outdoor air quality. And it seems to be a very open and shut case that it does make a big difference, but there's so many variations. So a lot of studies have shown that it is true that everyone knows that if you have a plant in your room, it does make you feel better and it does improve the air quality, it does remove the CO2. But what they've started finding is that different types of plants remove CO2 at different rates. So they found that some ferns are actually able to remove CO2 80% better than other types of plants that people would normally have in their house, which is probably why they're chosen so much as office plants as well, just because they're relatively easy to find and they are really effective. But it also works that they're really effective at actually removing VOCs and other carcinogenic compounds as well. So there's been studies showing that they can actually remove benzene, which is it's an overview essentially of most of organic compounds that we have in our homes and buildings. It's very effective at removing that. In some cases, it can remove all of the benzene available within a room within an hour if there's certain ventilation going through. So it's definitely something we should be looking to more in the built environment, is making sure we make the most of these green spaces, not only because they do improve the mood, but they massively reduce the amount of pollutants that we have in the atmosphere. And it's not just internal either. They work the same way outside as well. They're very good acoustic barriers. They're very good thermal insulators as well. And I know that moves a wee bit from the question, but I would put through that I think they should be a very effective way of doing it, and something we should look forward to doing more anyway with most construction.
Yeah.
Yeah, good.
And does anyone want to add anything?
I was going to say that don't forget that, of course, it's just pleasant to have plants indoors, right? Yeah. For most people, it's quite a pleasant situation to have plants. And I've read some of the studies done about productivity or CO2, whatever it is. I mean, the plant for sure is cleaning the air to some extent. We don't know how big the impact is, in terms of, for example, compared to ventilation or compared to, the first thing, of course, is source control. Don't have the pollutant in the space in the first place, right? So these are all things that come when you do have a source. But it's important to not underestimate how good it is for psychologically for people to have plants indoors. So I think that's also a big contribution of green walls or just your office plant.
Yeah, no, that's very interesting too. I'm doing my dissertation, and one of the topics is green walls as well, and how green spaces can improve not only the ventilation but also people's well-being. So for me, that's a very interesting topic. Now I'm going to move into a smart MVHR control. And the first question for you guys, any of you can jump in. What control strategies are most effective at reducing energy consumption for buildings in indoor environments? And I'm going to just face the question. So any of you can jump in.
So I'm happy taking the point on this one again. So one of the main things with regards to making sure we don't use too much energy is making sure we use actual comfort temperatures. So when we were in Dubai last year, it was 23, 24 degrees outside, maybe 29 in the middle of the day. A nice temperature, maybe a bit too warm for me, living in Scotland all of my life. But the biggest issue was you're outside in the heat and you get used to it, and you suddenly go inside and everything's conditioned to 14, 15 degrees, which is a massive temperature shock. and it's not what your body is wanting at that time. It wants a more gradual decrease. And one of the issues with that is they've designed a lot of the buildings over in Dubai are designed to British temperature controls. So in Britain, we will generally be happy in a room that's at 18 degrees, 19 degrees all year round because it's very close to our overall temperatures outside. There's no massive gaps. Whereas if you're in Dubai in the middle of summer and it's 40 degrees outside and you're going straight into a building that's 19 degrees, it feels like you're in an ice box. It's so cold. I got a cold. I actually was ill while I was over there because of how big the temperature change was. It made me very, very sick. So having an effective strategy is really, really important to make sure, first of all, the people inside feel comfortable, but also to make sure you're not actually overcooling a space. And that's something really important with the TMC project, especially due to the stringent temperature controls we have to face while we have the judging in the different sections throughout the competition. But just because, as we have such a limited source of power, being entirely solar powered, we have to make sure we use that energy as efficiently as possible. So making sure that everything's managed effectively is really important.
Yeah, I think that's an important point, Scott, because I mean this is a matter of culture, right? The culture of cool, right? That's a great book, by the way. If anybody's interested in the how, but mostly biased towards the United States, but how the culture of refrigeration actually developed by Marsha Ackerman. And it's very difficult to overrule that culture when outside is hot and muggy most of the time. People want the ice box, right? Even though it's not necessarily healthy or energy efficient for them. So yes, there is certainly some education or cultural change to be sort of gradually increase the acceptance of being closer to the outdoor. I mean, and this is only one generation or so that we've been living in these ice boxes. Before that, there was not really effective refrigeration, or at least it was not common. So you would go to the cinema hall to enjoy the air conditioning on the Sunday afternoon or whatever, and that's all you got. It's also important to remember that while it's not great to have airtight boxes from a pollution perspective, it does bring benefits in energy efficiency because now you don't have uncontrolled. So in Scotland, we have drafts, right? Cold draft coming in. That's very uncomfortable. Well, in places like Dubai, you will have sort of hot, dusty wind coming in. And so your house is just going to be caked with dust and it's going to have these warm, drafts. So building sort of, well-constructed houses, and of course with MVHR, which, we're going to talk about later, which at least when I moved to the UK from Switzerland, I was quite surprised how much resistance there is to MVHR in this country. Mechanical ventilation heat recovery, for those of you that are not familiar with that. And maybe Kelvin can talk a little bit about how they're using it in the Team Esteem project. But in theory, it works fairly well. You literally when you chuck out your stale air, you recover the heat from it. For the air that's coming in. So that's when you need the heat, right? And similarly, when you don't need the heat, you just, you get rid of it, you perhaps cool down the incoming air. So I think it's also important to remember that you can't rely on people to be conscientious about switching things on and off, which is why I'm very happy to hear about, the smart home efforts. It's as simple as geofencing, the Nest thermostat or Hive thermostat turns off the heating or the cooling when you leave the house. I mean, it's like, wow, that's a lot of these solutions are fairly simple, but they require continuous updating, monitoring, reminders, that kind of stuff.
Yeah, I think we're perhaps touching on the MVHR control. It's an efficient technology that's really reusing the heat that is generated by it and that's still in the air, and also distributing the airflow appropriately based on the motor speeds. So like basically we have those sensors networks, distributed sensor networks, to identify the temperature, humidity of the rooms, and then we can make control actions like on the predictions of those temperatures on a few time stamps ahead, and then we can control the motor speed of the airflow ahead using optimization algorithms. So I think that's where we would like to head with the sort of the way to control an MVHR system. But obviously there's different types of control mechanism or strategies you can use, like PID control, which is based on like past, present, and future errors in the temperature that controls the motor of the fans and the MVHR. So yeah, there's multiple ways about going control strategies, and even in the so my dissertation in the summer focused on mainly just the predictive elements to a model predictive control set of algorithms, and looking at different predictive algorithms. You can predict temperature and humidity. Looking if it was statistical methods gave you better forecasting error than sort of newer AI elements, or if it's you want computational efficiency with the amount of sensors you have in your network. But entirely, it depends on the amount of rooms you have, and the amount of spaces that your sensors you're really utilizing, and the sampling rates of them really. But yeah, it's a really interesting topic, and there's a lot of nuances and complexities to it.
I think that's an understatement, Kelvin, but yes.
Thank you, Kelvin. Thank you, Parag. So we are going to move to the last question, and then we're going to take questions from the audience as well, so we can let them talk. The last one would be, what effective, I'm sorry if I pronounce this incorrect, actuator optimization strategy to reach a set reference point for temperature or humidity? And is that? And anyone can take.
Oh yeah, so that was essentially what I was covering there. So like, in terms of the optimization strategies that I was that you can adopt, there's various ones. It's a big debate, I think, of what one's most effective in the particular environment, because you get optimization strategies like genetic algorithms to reach set reference points for temperature and humidity, which are based on like evolution, and basically how you need to recursively learn things to get to that point, that temperature point. And there's other optimization strategies as well out there, but I think that's something that we really need to look into, and with the controls guys at Arbenco, and work out what would be best for our home, really. What are your thoughts, Parag?
So I have a very, very civil engineer's perspective on this, which is that I just want my building to be nice, right? I don't need it to be complicated, right? So it's certainly the case that we are also looking at this, and we've been looking, with Kelvin, we've been working on sort of advanced control strategies based on optimization. And in theory, a lot of that actually works brilliantly, right? And when you write the code, you're like, wow, look at this kind of performance. If we had this performance, it would be fantastic. But then there's something when you implement this into a building, people show up, right? And then people turn things on and off, and people's preference changes, and their mood change, and what they want from a building changes. And I'm not saying that's bad. I'm saying, well, that's what people are. That's okay. That's what you're designing the building for. You're not designing the building so that the MVHR or the HVAC system runs properly. You're designing the building so that the people are happy, right? And sometimes people are happy when you give them a little bit of sunshine and a place to sit and write a note and drink coffee, and that's what you really need, right? So I think what my sort of, and I've said this before to Kelvin and Scott as well, is when we're exploring all this, you have to try and remember that the person using this, or the multiple people using this, are going to be, they're sort of sensors themselves. They can sense the surroundings. They're not very well calibrated. That's the problem, right? So when you think you're too warm, and versus, for example, Scott said we are happy at 19 degrees. I'm like, no, I'm only happy at like 21. 19 is a bit cold for me. But that's okay. I can still tolerate it. Some people are, but I could also go out for a run at 35 Celsius, whereas more Scottish people would be dead at 35 Celsius, right? So it's important to keep the human in mind, which is why when we talk about control at Arbenco, we talk about human-centric controls. Right? The fact that our control algorithm may be simple is not the problem, but it has to work for the person in the space. And if that means sometimes throwing out the nice theoretical stuff we just did, then so be it.
Yeah, it's about compromising pragmatism,
Exactly.
especially in the built environment and different structures of buildings, different insulation thicknesses, different.
Yeah, and not.
Yeah.
Sorry, I was gonna say, not to be. I'm not trying to be cynical about this. I'm not saying that we should stop. A thermostat is good enough, and that's all you need for the next few generations. Of course not. We have to keep improving the built environment, because clearly we're not delivering on the sustainable development goals, right? We're not reducing energy use fast enough. We're not increasing renewables fast enough. We're not making healthy buildings fast enough. So clearly something is going wrong, and we need to change. But for somebody like Carbon Co, some of the things we have to consider are, okay, well, once we've designed the system, how is it going to be installed? Who's going to install it? Are they going to understand it? Are they going to actually explain to the user properly how that system works? And how are we going to service that system? Which, if you think about it, distinct from, let's say, a phone or a computer, every building is unique, and yet it has to last 50 plus years, right? The system doesn't have to last 50 years. You'll probably replace it in about 20, 25 years, but 20 years is still a long time for a system to last. And there's very little, like software updates you can push over the internet and stuff, because lots of buildings are not connected. So those are the considerations that sometimes slow us down. But I certainly don't think that we should stop trying to change how buildings are currently operated.
Yeah, definitely.
Thank you very much. That's very interesting. Thank you. And now we will be asking our audience if they have any questions, and they can jump in. And I think Sonia had one, and so just Sonia, you can come into the call.
Hi, sorry. I think I will just pass on sharing my video right now, but just to read aloud the question I had, basically. So I'm wondering, in terms of really futuristic plans, do you think it's possible for the average house in the UK to have a control panel that does like a real data air analysis in terms of its components? And what I mean by that is to be able to detect any germs, so that you can have a real data visualization of what's happening in the air inside your house. And that's why I said it's a pretty futuristic vision, but very interesting.
I'll take the initial point on this, if that's okay. I think something like that will be implemented very soon after the current situation we're in, with everything that happens in stages, essentially gets massively boosted in situations like this. So an example would be the Second World War, massive technological advance that happened then. But another thing that's also happened very, very recently is the electric car boom. So 10 years ago, it cost you, I think the statistic is something like $1,000 per kilowatt hour, whereas now it's down to $150 per kilowatt hour, and the batteries can hold 5 times as much, and the car's traveling 3 times the distance. And it's just the 3-4 generations of batteries that have happened in the past 10 years has grown so rapidly because there's an appetite for it all of a sudden. And I think the same thing is going to happen with the current situation we're in, where the whole reason we're having this conversation is because of the education people want to have on how your buildings work and how everything is functioning. I think very soon it'll be implemented that it should be almost like what they're doing with the smart heating devices that are now going into new homes, of making people understand the heating loads and how they're using their energy, is understanding how they're building health as well as trying to implement everything else they're trying to do with all these zero carbon construction, as you mentioned briefly as well, Parag. So I think it's something they'll work towards. I don't know if the technology is there to identify individual germs anytime soon. I think that's a very, very long way away, especially because of how controlled you have to have it. But I think the idea that people will take a very keen interest in the air quality of their homes is something that will, I think, push very much forward with our generation in the next 10, 15 years as we start to move into the market of these sort of things.
Yeah, I completely agree with Scott there. So, to Sonia's question, there's 2 components here, right? One is whether you're able to measure viruses, and the second component is about displaying and the whole sort of ecosystem around it. So the second part is actually easier. And as Scott pointed out, we already have it. We can, even my company can provide you in an iPad an app, and you can have a kiosk. And hopefully that's what Team Esteem will show, one of the kiosks in the space. So of course that part is fairly well worked out. You can have connected sensing, you can have database management, everything goes through the cloud and all that stuff. What we don't have is continuous measurement or sampling of air for viral particles. Currently, the way we do this is through proxies, and the best proxy is CO2, because CO2 is an estimate. Well, CO2 is only produced by people in a space, right? And occasionally plants. So it means that if there is a high level of CO2, it means there have been more people, and those people would have also, along with CO2, emitted viral particles of whatever virus it was, right? Now, the problem might be that, okay, it's not great to breathe anybody else's viruses, but probably a lot of them are just harmless, well, relatively harmless, right? But once in a while, COVID-19 will come along and everything becomes much more problematic. So yes, it's very useful to measure CO2 like a proxy and say that, okay, well, if you just reduce the rebreathed fraction, so the amount of air that I have to breathe that somebody else has breathed before, that'll be helpful. But it's very hard to predict the future, because the system we developed in the last 3 years, I would not have been able to develop when I started my education, 10-ish years ago, because the technology wasn't there. And if it takes us 1 year to develop a vaccine during an emergency, maybe it also takes us a very short time, as Scott said, during an emergency to develop, at least sensors that can give you an estimate of viral load. You don't need it to be precise. You don't need it to be precise with the last single virus. You just need an estimate of the magnitude.
Yeah, I'm totally agree, Parag. I would say that in terms of COVID, like being just a trigger mechanism for indoor environmental quality health of buildings and indoor environmental quality air with the viral loads, just to assess that is going to be as key to make a roadmap and people will now invest and innovate more to get to that futuristic technology that might, sense every sort of particle in the room, work out exactly where they all are, but it's again going to be a long way off. It's going to be like economies of scale, like Scott was explaining with electric cars. It's going to take a lot of, but this COVID-19 situation might just be the emergency that indoor environmental quality needs for the future, really. And looking at working from home as well, so that pushing that as well. So now that people, you need to have a comfortable environment and to work productively, to work healthily as well. So.
Yeah, thank you very much. Not only that, I have seen some news about the World Green Building Council, and they are trying to do like the 7 frameworks where they prioritize the indoor quality environment as well. So yeah, we should be moving for better indoor air quality as well. And anyone has more questions? If not, I would like to thank everyone for coming, especially Parag, Kelvin, and Scott as well, because they were our finalists. And thank you, Sonia, for your questions. This will be recorded and will be posted next week, so everyone can see it and you can share it. Please, if you do have any question, we have our social media as well, Team and 2020, and of course, you have our Vinco as well. And thank you, everyone. And would you like to add anything, any message maybe? Any of you three? Maybe any message for future generation?
I was just going to say thank you very much for organising this, Iris, and again, thank you as well, Parag, for coming along. Brief conversations we've had, I think this was very interesting, and I'm glad we're all in the same boat, that it's something that is very interesting to look at more than anything else, and it's really needed just now, shall we say.
Absolutely. Thanks for having me.
Yep.
Thank you. Thank you.